Yeah, thanks for the invitation to speak. So I tried to make this seminar a little bit, I guess, materials project themed. So some of the questions I'll raise are sort of inspired by being a user of the materials project for quite a while. And I'm going to jump straight in. So for materials modeling, I think the typical workflow is that we want to map between structure and properties. So that's typically it. We use different codes, different approaches, but we want to make that mapping. And I think you can break it up into three parts. So usually we have an input that's a crystal structure. And often it's either directly from X-ray diffraction experiments, or if it's inspired by diffraction experiments. So you're taking a structure of a known material and maybe changing the composition or modifying the structure in a particular way. Of course, one of the pioneers in modern crystallography was Kathleen Lonsdale. Just pointing to her. And then we have to make a choice in the Hamiltonian. So the interactions that we want to describe in the system. And the interactions between electrons, between ion and electrons, for example. And of course, this follows Hamiltonian mechanics that was developed by William Hamilton. And then we want to think about the properties of the system that we care about. So it could be mechanical properties, optical, electronic. And I think the job of a computational scientist is really to choose the Hamiltonian that's appropriate for the system of interest, for that chemistry, for that structure type, and also for the property that you care about. So you might make a particular choice if you care about magnetism, and you could get away with sort of a model Hamiltonian that describes exchange interactions between electrons. And so you could predict, for example, magnetic susceptibility. But generally, in first principles materials modeling, we want to have a Hamiltonian that's as complete as possible. So we want to describe as many of the interactions in our system that we can to make the predictions as general as possible. And so that's a point I'll come back to a little bit later. But what I would say is that practically, we have to make choices. So choices that are pragmatic, that we can actually, we have a Hamiltonian that we can solve for our system in a reasonable time frame. And sort of going back to this early quote from Paul Dirac, so it follows, he said at the time that chemistry was a solved problem. So quantum mechanics has been developed in the early 20th century. And because the Schrödinger or Dirac equation can describe the electronic distribution of any combination of elements, therefore chemistry was solved. But the practical problem was the equations were too difficult to solve for any realistic system. So this is a quote from one of his papers. So approximate methods should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. And this really sums up the next century of effort in theoretical and computational science. So trying to reduce sort of the Schrödinger or Dirac equations, which describe all of the physics of the systems we care about, into a form that's tractable. And I think now typically we deal with sort of different sets of approximations. So we have analytical expressions, such as like a Leonard-Jones or Buckingham, where we have a closed form that describes the interaction between elements. So when the elements get too close, you get the repulsion. When you have sort of a sweet spot for the equilibrium bond length, and then you have sort of longer range van der Waals interaction. So that's sort of the Leonard-Jones type. Of course, that's very straightforward to deal with computationally. So now we can have classical force field simulations for systems of millions or billions of atoms. So still very powerful techniques. But maybe the majority of supercomputing time, at least public supercomputing time right now, would be spent on numerical solutions of, for example, the Kohn-Sham equations. So there we make particular approximations to make the equations solvable for sort of systems that we care about. So usually systems ranging, I guess, from a couple to hundreds or sometimes thousands of atoms. And then more recently, we have a whole new set of statistical approximations. So using machine learning, we can also describe interactions between elements. We can describe structure and composition property relationships. And so this is really taking advantage of machine learning models as function approximators. So if we don't know the exact function that relates the input structure to the output property, perhaps we can train a model that will, a machine learning model that will describe it. Okay, so that was Paul Dirac in the late 1920s. If you move forward a few decades, at that particular time, so there's really the development of modern computing started, and Charles Coulson wrote a very nice essay on a split in the field of theoretical chemistry. So those theoretical chemists that were focused on having accurate analytical solutions of sort of quantum mechanical problems of several electrons interacting. And there was a group of people working on sort of approximations to allow us to treat larger and more complex systems. But he worked out sort of the information that you would need to encode to describe the interacting wave function of 20 electrons and figured out that that surpassed what would be possible in the foreseeable future. So he made this prediction that around 20 electrons would be an upper limit to what would ever be possible to calculate. And of course, he couldn't really see what was coming in the future. And these days, it's becoming possible to solve sort of Coulson equations for systems of definitely hundreds or thousands of electrons. So for example, this metal organic framework, UIO66, if you're treating it in an all-electron simulation, the unit cell has 752 electrons. But yet we can do it now for two reasons. So one is that we have much larger computers. So if you look at top 500, so the ranking of public supercomputers, we now have many systems with over 1 million processors, which is quite incredible how quickly the complexity of supercomputers has grown, including some nice ones in the US. But you also have to pay attention to the power usage. So some of these, like taking sort of 29,000 kilowatts of power for the #1 supercomputer, that basically would require an old-fashioned coal power plant just to power that one supercomputer in terms of the capacity. So it's definitely something that's playing on my mind in terms of how we can be as efficient as possible in our use of resource. And I think databases such as the Materials Project is one way that we can reduce sort of the need to keep rerunning the same calculations over and over. So definitely on one side, parallel computing is playing a big role in being able to sort of brute force solve these equations for larger systems. And then of course we have the algorithms that are sort of powering them. And a common bottleneck in first principles modeling is simply matrix diagonalization. So as a matrix gets larger and larger, so as you have more basis functions, it becomes much more difficult to distribute that task on many processors. But there has been a lot of work in applied maths and computer science in making this more efficient. So I use the code FHA AIMS a lot, and they've been involved in the development of this ELPA library, which has been really impressive in the rate of progress. That now, so you can start to diagonalize a matrix that has more than of dimensions greater than 500,000 using sort of over 20,000 cores quite efficiently. So it's really thanks to hardware and some of these software developments that we can start to go beyond treating very simple systems using DFT, start to treat things such as dislocations and grain boundaries that wouldn't have been possible even 5 or 10 years ago. So that was a little bit of context. So I said this seminar I wanted to make a little bit bespoke, and I've broken it up into at least past, present, and future, as I see it in terms of materials modeling, but sort of drawing, I guess, from my progression over the years. And so I started my PhD about 20 years ago, and I think a lot has changed since then. And that was really when we were doing one compound at a time with DFT. So these calculations were very expensive. We're using reasonable supercomputing clusters to solve Coulson equations for relatively simple systems. So my PhD was focused on understanding connections between chemistry, crystal structure, and physical properties, with a strong focus on post-transition metal compounds. So looking at, for example, the differences between tin dioxide, so SnO2, versus tin monoxide, so SnO. So large changes in the crystal structure, in the band structure, and in the semiconducting properties. And towards the end of my PhD, we actually got a new supercomputer in Dublin. I actually can't remember the size right now. But it enabled us to do larger calculations than ever before. So I was very excited to work on this system, bismuth-stannate. So this was the most complex inorganic crystal structure that had been solved from powder diffraction at the time. So I think over 300 atoms in a unit cell. And so we're able to solve the electronic structure and look at some of the interesting features associated with this bismuth lone pair. So you can see this asymmetric electron density. But at the time, it seemed like very fundamental work, sort of just looking at interactions between bismuth and oxygen and bismuth and sulfur. And it was just later in my career, somehow these lone pairs kept coming back. So applications in terms of electrocatalysts and photocatalysts and solar cells, a range of materials, these sort of lone pair states ended up re-emerging, primarily as a way to increase conductivity and increase absorption in the visible range of the electromagnetic spectrum. So systems like bismuth vanadate are being quite widely used as photocatalysts for water splitting. But that was my PhD. But for my postdoctoral research, I wanted to get a little bit more applied. So I ended up moving to Colorado to work at the National Renewable Energy Lab, where my focus was on high throughput simulations. So there I had access to much larger computers, thanks to the US Department of Energy. And we could think about running many DFT calculations. So orders of magnitude more than I was doing for my PhD. And at the time, I was quite inspired by mineral structures. And the idea of taking these sort of prototype structures, for example, here is the casterite mineral that can be found in Russia, and thinking about substituting in alternative elements and looking at the possible chemical space that could be formed inside those mineral structures. And that was a really fun time. So casterite actually forms a diamond-based superlattice. So you have this sort of zinc blende diamond structure that you can populate with a single element, it's diamond, 2 elements, it's zinc blende, 3 elements, it's chalcopyrite, and 4 elements, it's casterite. And then you can think about the possible chemical space that you can access by substituting in those elements. So of course, there are a number of known compounds, binary, ternary, quaternary, but there's also a large number of unknown that perhaps could be made. So I spent a long time exploring and performing many such calculations. And a really cool thing, so within that single crystal space, we identified potential materials for solar cells, spin transport materials, so very strong spin orbit coupling, and also a family of topological insulators. So that was a really productive time using DFT to be quite exploratory in terms of crystal space. But what I would say, so I was trained formally as a computational chemist, and you can see I was getting quite deep into condensed matter physics. So I had a chance, I got a Marie Curie fellowship to move to the UK and sort of think about my research direction a little bit. So I decided to combine my interests in chemistry and physics and devote some time to organic, inorganic systems. So paying attention to some emerging activity in the field of hybrid semiconductors. So materials formed from inorganic and organic building blocks, but yet they could still conduct charge. So quite different to the sort of first wave of metal organic frameworks that were very much wide bandgap dielectric insulators. So systems such as this, so this sort of mixture of lead sulfide and these sort of aromatic rings, and you can give rise to very low effective masses and some quite high levels of conductivity. And that ended up being quite a strong stream of research for me. So trying to translate concepts from semiconductor physics, so things like band engineering, to the field of hybrid solids or metal organic frameworks. So in this particular case, taking quite a wide bandgap, but yet photoactive crystal, and making a series of substitutions on the ligands to try to control the band energies. So that was a pretty fun time. But what I would say, sort of back then, 10 years ago, it was incredibly difficult to set up calculations for metal organic frameworks. So often the structures you get from experiment are quite incomplete. So usually missing hydrogen, And quite often you have partial occupancies because of how they refine the structures. That you have some sort of orientational flexibility in ligands. So then they end up fitting a 50% site here, 50% site here. So there was a lot of manual effort to actually parse the experimental CIFs into something that you could run a DFT calculation on. So it's been really nice to see a lot of progress in that area to make these types of frameworks more tractable. I think one nice initiative came out from Northwestern, CORMOF, which is a data set of computational ready meta-organic frameworks. So trying to add hydrogens, removing disorder, and having a list of structures that you could really plug and play. And then, of course, this year we've just seen a launch in materials project, so the MOF Explorer, and again, incredibly exciting to be able to go through so many different MOFs and see the range of predicted properties. And so I think Andrew Rosen, he did a really nice job with the QMOF database, which was published last year, the year before, and has implemented this in the materials project. So I think this is a really nice feature for people working in the area. So that was really when I was starting my research group. And I still remember my first PhD student. He was a few months into his PhD and he came to me and said, Aaron, we're in trouble. There's a website that's already done the calculations you asked me to do. And so this is Lee Burton, and his PhD was focused on tin sulfide solar cells, so SNS related. And so one of his first tasks was to sort of perform some thermodynamic calculations and come up with a convex hull for the tin sulfide system. And so he found materialsproject.org and found actually there was a convex hull there already. And he was a little bit depressed because he's like, now what am I going to do for my PhD? But still, there was a lot more to do. There was extra phases. There was quite a strong sensitivity to the functional. But nonetheless, that was my first, I think, introduction to materials project. And for me, it was quite eye-opening. So it was a real shift in mentality. So it sort of standardized a lot of the ground state sort of DFT calculations of perfect crystals and raised the bar for the types of research problems that we could start to tackle. So instead of reproducing all of these sort of simple reference systems, why not use that data and try to do something more interesting? Okay, so that brings me to the, well, closer to the present. But what I would say, my next step, so once I found materials project, that made me think about materials data and thinking about even larger chemical spaces. So I ended up going back to some of the quite early research papers I had been reading when I was working at NREL. So work in the 1950s and 60s, when people were thinking about electron counting related to semiconductors. So there was a number of semiconducting families, so binary, ternary, some quaternary, that had been characterized at the time. And people like Brian Pamplin started to think about actually what other semiconductors could exist. If we take into account sort of valence electron counting rules, there should be a whole range of multi-component semiconductors that should be accessible. But at the time, it was really just based on electron counting. There's no other metric to say, sort of, would those materials be chemically sensible or would they be stable? So that inspired us to put together, I think, a relatively simple package called SMACT. So Semiconductor Materials from Analogy in Chemical Theory. So directly inspired for the work of Brian Pamplin and others at the time. But the idea was to put together a package that could deal with elements and some simple chemical features so that we could explore spaces for sort of millions of combinations and try to filter which ones could be feasible or not. And I think the first person to commit some code was Keith Butler. He was a postdoc in my group at the time, and now he's a staff scientist in the Scientific Machine Learning Division at SDFC, so a UK national lab. And then we had many contributions from undergraduate researchers. So I found this was a really great way to introduce Python and introduce some basic package management to various students throughout the years. And I think Dan Davis was one of the main contributors, and he worked on SMACT during his PhD. And I think he had a visit to Berkeley towards the end of his PhD. But many other contributors along the way, and Anthony, he's working on SMACT right now. But I think the key approximation at the beginning was really trying to simplify the problem of exploring chemical spaces. So saying, okay, let's ignore structure. Let's try to explore and build models based purely on composition or element features. So can we look at balancing charge, balancing electronegativities, having some metrics for stable oxidation states, and things like that. So that was sort of the approach that we followed. But towards the end of his PhD, Dan, I think he was getting quite ambitious in terms of, okay, if you want to start to make strong predictions that could be verified experimentally, you really have to integrate structure. So then we started to work on metrics for predicting structure quite efficiently. And so one of the bottlenecks Dan had faced was the lack of description of structure in trying to train element-only models. And the issue that you really have is the inability to describe polymorphs. And so here is just a distribution of band gaps in the materials project for materials with the same composition. So it's looking at the spread in band gap as a property across different polymorphs. And you can see for some materials, there's actually quite a large difference. So you can have up to a 2 electron volt difference, the same composition in 2 different structures. And so this is going to set a limit to the accuracy of any derived models that don't include structure as a feature. And so that made us sort of take a step back and really think about integrating more structure features and more sophisticated or faster ways to predict structure directly from compositions. But I would say since then, back in 2019, of course, there has been a lot of progress in more complex elemental features. And I'm sure Taylor Sparks will talk about that next month. But in terms of encoding sort of more than just the sort of elemental identity into a structure feature. But I just wanted to give one example where I think structure has been very important in my sort of recent work, and that would be the perovskite system. And probably many of you, whether you like them or not, you've come across the perovskite structure at some stage. But the simple sort of high symmetry prototype is relatively straightforward. It's a cubic structure, a primitive unit cell with five atoms in the basis. And the crystal structure was determined back in 1925 with the structure of the mineral form of calcium titanate. But the interesting thing about perovskites is not that cubic sort of parent structure, it's all of the derived lower symmetry structures that can emerge from that. And so it's been shown that there's 23 distinct types of lower symmetry perovskites that can emerge from tilting of those octahedra. And you can connect them according to group theory. So you have the high symmetry cubic structure on top. Then you start to remove particular symmetry elements. So you can form a tetragonal structure, remove another symmetry element, form an orthorhombic structure, another one form a monoclinic structure. So you have this family of related structures. They're all based on ABX3. They're all based on connected octahedra, but it's just the deformations of those octahedra that vary. But my particular interest has been in the subclass of hybrid halide perovskites. So these gained a lot of attention for applications in solar cells and LEDs, and even these days for memristors and other applications. And the difference here is that one of the elemental components of the perovskite is replaced by a molecule. So it could be something like methylammonium or formamidinium or DMA or MDA. And so different molecules will sit on a lattice site that is occupied by a charged ion in a regular perovskite. And the really interesting thing is that these materials, so if you have methylammonium lead chloride, for example, and they still occupy the regular perovskite structures. So these colors represent different compositions that have been reported in various space groups corresponding to tilted perovskite polymorphs. So a lot of the previous knowledge in terms of the crystallography of oxide perovskites translated very well to the family of hybrid halide materials. But one of the first things we noticed when we started to sort of look at these in a little bit more detail is that although the X-ray diffraction tells you one story, maybe there's a particular high symmetry perovskite structure that's present, When we look locally, for example, when you do molecular dynamic simulations, you see a lot of disorder. So you see librations and rotations of the molecular building blocks, and you see a lot of motion in the underlying, in this case, lead iodine framework. So a lot of things happening, and it made us realize that these structures are highly dynamic, and they're not fully described by Bragg diffraction, which is really an average over space and time. So if we look at the distribution of the ions in the system from room temperature and molecular dynamic simulations, what you see, okay, the average crystallographic position is indeed at the center of the distributions, but you have very large deviations from the average positions. And at the beginning, I would say we're a little bit confused about these sort of very elongated ellipsoids around the iodine positions in the structure. But of course, it makes a lot of sense when you think about tilting of octahedra, because this tilting sort of maps out an ellipsoid rather than a sphere. So you have these very asymmetric lobes that are mapped out from the ion distributions. And so we were sort of shouting to the community a little bit about some of these features, and it managed to get a very nice collaboration with the group of Simon Billinge at Columbia University in New York. And so he's an expert in inelastic scattering, which is a way to probe the local structure. And so we got a very nice validation that indeed, although Bragg diffraction was telling us one thing about the symmetry of these halide perovskite structures that are sort of quite averaged, locally there's a lot more happening. And essentially from the inelastic measurements, you can analyze a pair distribution function. And what you find is that over different length scales, you have a best fit to different crystal structure types. So when you look over long length scales for this particular material at this temperature, you get a best fit to a cubic perovskite structure. But when you look over shorter length scales, you get a best fit to a polar tetragonal space group. So there's a difference between the short range features and the long range behavior. And so that was back in 2016. But since then, I think experimentally, we've been able to probe over shorter and shorter length scales in very nice ways. And so I did a collaboration in this case with Tiernan Doherty, who's a PhD student with Sam Stranks in Cambridge. And they've been using selected area electron diffraction to take some very high performance perovskite solar cell films and look at the changes in structure within a grain and between grains. And remarkably, they can see several things. So you can see strain gradients within a grain. So you see that the effective lattice constant varies within a grain. So you have built-in strain in these high performance films, but also you have a range of different polymorphs that coexist. So you can have tetragonal phases, you can have hexagonal polytypes, you can have cubic phases that all coexist within these high performance films. And so these perovskites are extremely heterogeneous. So this is really pushing us to think how we can model such things. So the mixture of phases that are present at once in these films at room temperature. And so thinking about larger scale simulations and how we can map out these local distortions in a more efficient way. And so my student Kazuki Morita, he spent quite a bit of time thinking of how he could efficiently featureize distortions in octahedral systems. So going back to some simple group theory and the possible ways that you can deform an octahedron. So he realized there's actually only 4 unique modes. So you can take any octahedron, and if it's distorted, you can map it essentially into 4 dimensions. So this ends up being a very convenient way to, if you're given a set of structures, either separate structures or a structure that's very large, and you have a series of distortions over space, this is one way that enables you to classify those distortions. And so to test the protocol he put together, so he initially looked at ABO3 octahedra inside the materials project. So he's able to extract 552 octahedra. And this is the distribution of distortions. So the index of those 4 modes for those octahedra. And so you can see quite a large spread. So you end up getting a peak at 0 when you, for example, if you have a cubic polymorph, So you have a perfect octahedron. So it could be rock salt, it could be a cubic perovskite. Then you have no distortions. But there are a number of structure types and materials that exhibit large distortions over quite a large range. So this was quite cool, that we could see that a series of distortions were present. And digging a little bit further, Kazuki found that distortions classified very nicely according to the connectivity between octahedra. So whether you have corner sharing networks or edge sharing networks or face sharing networks or some combination of corner sharing and face sharing. So the distortions really broke down into these separate sets. And so in this case, you get the strongest distortions in the combination of these two particular modes when you have a mixture of corner and face sharing connectivities. And so, yeah, there's some quite nice findings in that particular paper, but I don't want to draw on it too long. But what Kazuki found, quite surprisingly, and this is really thanks to one of the reviewers pushing us to do this, so he performed a series of molecular dynamics simulations for some halide perovskites and found that a very simple supervised model that just tried to reproduce the energies from the MD, so a really minimalist model where the only features were the distortions of the octahedra, did a very good job. So with 4 dimensions, you could get a very good fit to the energies. So this just shows that group theory can be quite useful in terms of informing us in efficient representations of structure. So there's a lot of knowledge built in crystallography that we can remap to have more efficient models for training in machine learning. So yeah, we're using it for molecular dynamics, but we're also applying it now to look at more complex perovskite polytypes. So Zhenju Li's a postdoc in my group, and she's wrote a nice package for generating very complex perovskite sequences. So where you have mixtures of different connectivities between corner and face sharing. And so sometimes it's described as a mixture of cubic and hexagonal polytypes. And then we can perform various analyses to see what type of distortions emerge. Because there's increasing evidence that these types of intergrowths appear both in oxide and in halide perovskite films. So because you have a very delicate balance between sometimes these hexagonal and cubic networks, that in reality at room temperature, you end up getting some mixture of the two. So that's a really fun topic that's sort of attracting our attention. Okay, that brings me to the future. So to get back to my title of the ground truth. So I mentioned, I can't remember exactly what the title was, but something about the ground truth is out there. And so when you think about the ground truth of quantum mechanics, so I think we're really lucky in a way that compared to many other fields, we have the ability to generate our own data. So we can make predictions, for example, with a machine learning model of a particular property, but we have the ability to calculate. We can go back, we can solve a set of equations and predict what that value is. So I think that active learning is really going to be a very exciting opportunity in materials design in the future. But nonetheless, so ground truth of quantum mechanics. So what we want is a complete description of all interactions in our system. So if you think we have a crystal, that crystal has atoms sitting at particular sites. We want to describe all the interactions between atoms in the particular crystal that gives us exact properties of the system. So you can start to write down the Hamiltonian that may include all the interactions that you need. Usually the first term is the atoms sitting at their positions. That generates a periodic potential. That periodic potential distributes the electrons. That defines the chemical bonds. And from that, we can determine the energy. So that would be the internal energy of the system. But depending on the system, if you have a small gap, or if it's a magnetic system where you have different configurations that can emerge, then you have excitations. If they're low energy, they're going to perturb that static crystal potential. You also have vibrations. In the simplest approximations, you have harmonic vibrations. The atoms are moving in a harmonic potential. So then we have a number of almost analytic terms we can incorporate to modify the energies, to modify the properties. But increasingly for materials research, we're driven in a direction where anharmonicity is becoming increasingly important. So if you're interested in thermoelectrics, it's all about tuning thermal conductivity. Thermal conductivity is only defined when you have these anharmonic terms. So you also have to include some description of anharmonicity. And then you have coupling between vibrations and the electronic states. So you have electron-phonon coupling to incorporate as well. So you think about this mega Hamiltonian that starts to describe all of the interactions that are at play to describe the properties that a material has at finite temperatures, which is sort of real temperatures at room temperature. But often what we do, mainly because it's convenient or it makes our job a little bit easier, we strike out all of the other terms. We say, okay, let's just keep the static potential. Let's assume we have a crystal that's static. The atoms don't move. They are the properties. Job done. That's okay in some cases, but of course, we're missing many things. We're missing free energies. So we don't have any temperature or true pressure dependence in the phase diagrams. And we're missing thermal expansion, which could be positive or could be negative. It might be isotropic, it might be anisotropic. Thermal expansion can have a big effect on properties, whether it's mechanical, sort of changing a bulk modulus, whether it's changing a band gap. And basically every property is going to depend on how a material expands. And the halide perovskites I mentioned before, they have some of the largest thermal expansion coefficients of any known solid. So you end up having very big changes in structure at room temperature. So if you do a static calculation, and I say here athermal because we have no description of temperature, not even 0-point motion, then we have a built-in error. And of course, explicit electron-phonon interactions can be very important in some cases as well. So we have all of these extra terms that we may want to include. And of course, there are ways to include them. So for example, if we go to the quasi-harmonic approximation, this is sort of a cheap and cheerful way to include the effect of temperature. So you have a free energy that depends on the volume of the system. And essentially what you do is minimize the volume for a given temperature. You find the volume that minimizes the free energy at a given temperature. So for these rock salt systems, you have the lattice constant that changes with temperature, and therefore we can look at how a property changes as the structure changes. And in this case, a bulk modulus can easily change by about 30% when a crystal expands from 0 Kelvin to room temperature. I say cheap and cheerful. Quasi-harmonic works quite well for many cases, but still it's quite approximate. One of the reasons is it can't describe changes in internal degrees of freedom very well. So you have to go beyond the quasi-harmonic approximation. And in terms of describing these sort of anharmonic contributions to structure, to free energies, to properties, there's been an incredible amount of progress over the past 3 to 5 years in new methods, but many of them are using things like compressed sensing. So instead of explicitly calculating all the terms, you can sample the anharmonicity and come up with some effective correction. And so at Tadano in Tsukuba, he's been doing some really nice work developing the Alamode code to include some of those corrections. And so he published this preprint last autumn. So looking at terms that are missing in the quasi-harmonic approximation. Very interesting to me because before that, we knew there were some things missing, but the quasi-harmonic approximation is a little bit peculiar because it's not part of any formal expansion in terms of many-body theory. So it sort of combines a mixture of different terms, but this paper he actually tries to quantify what terms are missing. And what's quite curious, even systems like sodium chloride and magnesium oxide, they're classified as strongly anharmonic. So at least me, I'd have the intuition that a rock salt crystal should be quite robust. You don't have to worry too much about anharmonicity, but actually it's not the case. There's a lot of interaction between vibrations. That's, I think, one dimension you can look down. And just hot from Twitter. So this particular tweet caught my attention yesterday. So Maya wrote, "I don't like people who neglect spin-orbit coupling. That's it, I've said it." And I felt a little bit hurt. Like she could have been talking to me, because there's many cases where we have to neglect spin-orbit coupling because it's expensive, not because we don't know it's important. So for example, in the halide perovskites, which contain lead, we know spin-orbit coupling is important, but primarily it affects the conduction band, where the p band that's formally empty. So we can make assumptions that maybe the dynamics are not so much affected. Molecular dynamics should be okay, vibration should be reasonable, and we do have some evidence to back that up. But generally, it can be difficult to justify why we neglect such effects. And in fact, a few years ago, this actually reminded me. So with Dan Davis, I had a collaboration with Anubhav, sort of looking at some trends in spin-orbit coupling. So taking sets of materials from the materials project, including spin-orbit coupling, and looking at the impact. And here's a series of plots. So they're band gap differences. So the difference in band gap calculated with spin-orbit coupling and without spin-orbit coupling. And there's a general assumption that spin-orbit coupling is a constant for a particular element. So if you think you have lead, you have tin present, it's going to result in some correction that you need. Add a shift in the chemical potential, add a constant term, and that's going to fix your calculations. But what we found, quite scarily, that there's actually quite a large distribution for these heavy elements in the corrections. So just looking at lead, there's variation between no band gap shift down to a 1.4 electron volt band gap shift. And initially I thought that was a bit strange. And so I got Dan to break it down in terms of oxidation state. So you see, actually, there's many more lead-2 compounds. So most of the distribution is in lead-2. Then I thought, okay, it must depend either on the coordination environment or on the anion that's present. But yet we couldn't see any clear correlation. So that's what these plots are trying to show. And I think the timing was a little bit early. We didn't have any good sort of featurization of structure that we could have plugged in. And I think this could really be revisited with some supervised machine learning to try to identify some particular correlations to see what features are driving these distributions. It could also be that the data was slightly anomalous. That's possible as well. But still, it shows the spurious errors that can be built in when we choose a fixed Hamiltonian and expect it to be transferable for many materials. So this got me thinking. But maybe just from another perspective, so in terms of materials data and databases, so I think from the user, of course, we want to have absolute data. Please do the best quality calculations you can. Give us the best data so that we can use them in our trained models or infer for sort of our various predictions. So you can think of it like a Jacob's ladder. So we want to get up to heaven. And that's from the user perspective. So we want the best data possible. But I do realize from the curator perspective, so if you're maintaining or running the calculations with these databases, it might be more similar to a Dante's Inferno. So you have all of these rings of hell that you have to get through, because different approximations, it can be tricky. You end up errors crop up for particular chemistries that you can no longer avoid. And you can have other issues. Maybe a pseudopotential cannot be used for that particular type of calculation. So it's very difficult to have systematic data for all materials. So there is a balance there. But what I would say, so how I'm using materials databases and materials project and PyMatchN at the moment. So just to give you an idea. So I'm using it in my undergraduate teaching. So my first year undergrads in materials at Imperial, they all get to use materials project in the introduction to crystallography. I get them to make their accounts, to download structures, to play with those structures. So that's really, really useful. For my postgraduate teaching, I typically get them to use the Python API. So to actually get an experience of queries, of extracting data from databases. Again, very, very useful. And then for research projects, I love the website. For informal project planning, so during seminars, if somebody mentions an interesting compound, I'm straight to materials project to check it out, some basic properties. And then, of course, for data-driven projects, having that resource of systematic data is invaluable. So I really appreciate all of the effort that goes into maintaining such a database. So both in terms of the energies, but also the structures that are there. But then on the other side, of course, you do have some perils. I think many people enter this field, perhaps not from the computational science background, and sometimes they may have the belief that this data is absolute, that these are the energies, these are the band gaps, these are the phase diagrams. That is the truth. If I build a model that can reproduce it, then I've solved everything. But I think we know that's not really the case, and that there can be many hidden errors. But something else that actually caught my interest recently. So some of you may have read the book from Christoph Molnar. So he wrote a very nice open source textbook on interpretable machine learning. So the various approaches that you can use to open up black box models in different ways. And so he posted this recently. So I think he's become a little bit cynical about machine learning in general. So this is not specifically for materials, but that machine learning research has detached itself from solving real problems and created benchmark islands. That there's these very large data sets, and it seems to be what people want to do is just develop models that can reproduce those data sets with less error. And so he highlighted a number of what he called warning signs. So that predictive models is its sole measure of progress, that the original motivations and assumptions for developing these models are no longer questioned, and the actual progress in solving the overarching research questions have become irrelevant or even discouraged. I don't think we're there yet for materials. I think we're really at the formative stages where people are taking different models, seeing how they work, trying to develop more accurate approaches, more general, more transferable. But I think it's quite useful just to pay attention to these warning signs. As an editor, as a reader, I do come across a number of papers where sometimes I read them and think, is that useful for me as a solid state chemist or physicist? But yet, they can be useful in terms of developing the general infrastructure. But I think sometimes we have to think about these overarching questions of the big problems that we're trying to solve. And I think one of them, at least for me, is thinking about new chemical spaces. So often we're looking for materials with particular properties or to meet a particular figure of merit. And I think there are an increasing number of daft predictions in the literature. But sometimes we have a set of very powerful tools. But we just need to have that balance between sort of exploring new chemical spaces and being careful in what we're saying is going to be the next great material. And I think Alex Zunger was really on point in this commentary in Nature a few years ago on the burden of proof that we have as materials modelers when we make predictions of a new system that has a particular property, making sure that it's as realistic as possible. And I think at this point in time, so we have many indicators of stability. So you can think in terms of thermodynamics, of locally heat of formation. It's usually quite optimistic. You can think globally about convex hulls, maybe an open environment interaction with oxygen or water. You can think kinetically about the phonons, it's usually quite small displacements. You could think about molecular dynamics or maybe even Monte Carlo methods, or come up with a model for synthesizability for machine learning. I think we have many indicators right now, but personally, I haven't seen a quantitative stability figure of merit or machine learning model that I'm really convinced by. I think it's really very much a work in progress, and I'm excited to see where the community is going to go over the next few years in terms of being able to predict these realistic candidates more efficiently. And I really enjoyed reading actually one paper from Berkeley, I think it just appeared this year, from Christopher Bartel, reviewing some of the approaches for stability metrics. So thinking about different thermodynamic potentials that we can incorporate in terms of having more accurate and reliable predictions. So apologies for the rant, but that was sort of a series of things that were just on my mind recently. And that sort of brings me to the end. So thanks if you stayed till now, that's great. So what I tried to get across was the predictive power of materials modeling. I think what I've seen in the last 20 years is incredible in terms of going from these individual calculations, solving Coulson equations, to now thinking about tens of thousands of materials. But at the same time, I think we need to be critical of the models that are being developed and also of the data that we're training those models on, if we're going to have robust and meaningful predictions in the future. So thanks to my research group, collaboration network. I know Roshi Yang, one of my PhD students, she's working hard over in Berkeley. Thanks to everybody else. I think Materials Project community has been quite forward thinking in terms of reproducible science. So I'm not going to dwell much in terms of sharing your codes and data, but thank you all for your attention.
Great, thank you so much, Aaron, for the wonderful talk. We do have some questions in the Q&A panel if you're able to go ahead and review those. Apologies to anyone whose questions we're not able to answer in the next few minutes, but we will have the link open in materialsproject.org/seminars where you can repost the questions. So Aaron, are you able to see the questions? Would you like me to moderate, or are you able to see them yourself and we can try to answer some of these?
Let me just get my screen going and it should be fine. Yeah, go for it. Oh, I can see them. So do you want me to just go through?
Sure, yeah, in any order you'd like. So.
Okay, so and Abhav, you're an expert on this topic, so feel free to chip in as well. So there's one from Gabriel Mann. So can one predict, based on atomic number alone, which elements have chemically active versus inactive lone pairs? I think that's a really good question. And it's actually the one I gave to Kazuki at the beginning of his PhD. He's coming to the end of it right now. And back then, I think it wasn't possible in order to get a very sort of good clustering. There seems to be this very, very delicate balance. So even what I'm seeing in the lead halide compounds, there's a very large family of lead iodide systems with different counter ions. And with some counter ions, you end up getting an inactive lone pair. So you get a regular octahedron. In other cases, then you get this very projected lone pair. So more sort of this deformed either 4 or 5 coordinate environment. And I think there has to be a chemical explanation exactly why, but I haven't seen a good prediction yet in terms of classifying the behavior. But I think that's a really, really good question. So thanks for that, Gabriel. Second question from Robert Wexler. So there have been some very impressive advances in using machine learning to fit interdynamic potentials or solve the many-body Schrodinger equation. So these models, however, tend to be black box, which based on your talk today isn't always desired for an intuition in materials design. What's my perspective? Am I optimistic that simpler theories for materials design will be discovered in the next decade? So personally, I think machine learned interdynamic potentials are quite game-changing. So I've been involved in quite a number of projects in trying to train new classical potentials. So taking some Buckingham type potential, you have a set of observables, you try to find a set of coefficients that fit this particular functional form. And it's a nightmare. So it's often called the dark art, that it's so difficult to train a new interatomic potential. So people spend years trying to, even a system like titanium dioxide, there's no robust interatomic potential for titanium dioxide that can describe its various polymorphs and its instabilities. But machine learning, if you're thinking about sort of these sort of Gaussian approximation type potentials, they seem to do an incredibly good job with relatively little data. So instead of having a set of clear observables, you just sample a set of perturbed structures, you train an effective model, and it does a really good job. So I think, especially when you're treating with systems that are polymorphic, if you have, for example, a crystalline to amorphous phase transition, if you have some complex behavior that you want to describe, these seem to do a really, really good job. So I think for those types of materials, it's going to be very useful and will go beyond sort of solving the Coulson equations. Because you see, they're not interpretable, but even DFT is not very interpretable either, in terms of you're solving this set of partial differential equations that does map between structure and properties, but the interpretation is usually up to the user. So do you interpret the system as covalent or ionic? Are you using sort of a COHP type approach? There's many different ways. And I think machine learning is just like that. And I think the general trend is more interpretable models. So I'm very optimistic for the role of machine learning right now. So a question for Baha Kahil. So can we use synthetic data to fill in the missing pieces? So in principle, yes. I think it really depends on the type of project. I think like others, we've tried to do natural language processing to, for example, extract data from the literature, but you run into problems quite quickly. So if you take a material like zinc oxide and you try to do data mining of bandgap, you'll get a very large range because different groups have different samples that have different impurities, different thicknesses, different morphologies. They fit their optical absorption in different ways. So you get a very large range in the values that have been reported. And so I think there's a lot of hidden variables in the experimental data that are difficult to extract because they're not in the papers themselves. So what were the background defect concentrations? What's the dominant orientation of the crystals? What's the particle size? So I think it's difficult, but I think if you have a focused project where you're really trying to calculate something that's directly being measured, then I think it becomes very useful to combine synthetic and predicted data. But if you're trying to do it blindly from the literature, I think it's very, very difficult. So I hope that answers your question. Next question from Gabriel. Gabriel is back again. Given a standard halide perovskite, so methylammonium lead bromide, what are the smallest and largest terms in the Hamiltonian? Oh. How large is the anharmonic term relative to static potential term? So this is actually one of the really big questions right now. There's many high-profile papers talking about the high levels of anharmonicity. I think generally for these materials, if you perform a harmonic phonon calculation, so you calculate a set of frequencies, typically the agreement is reasonable with respect to experiment. So you get infrared and Raman peaks that are reasonable, but you also get a number of imaginary modes. So imaginary modes that correspond to these tilting of the octahedra, some dynamic instability. So that's what the anharmonic theories allow you to capture. So I think in many cases, the room temperature phases are stapled by anharmonic terms. So at low temperature, you have a very rigid, heavily tilted perovskite. At room temperature, they're heavily dynamic. That dynamic behavior is inherently anharmonic. So you need to have a double well type potential. But still, I think if you're really asking about the order of the terms, the anharmonic results in a large contribution to the free energy, but it's not enough to describe the room temperature phases. So you have to go beyond. But I think that's a topic that's still under active research and debate right now. Also, greetings to Jacob Gavartin, who I think is that Schrodinger these days. So Aron, thank you for the thought-provoking talk with regards to the group theoretical analysis. You mentioned that these distortions are of Jahn-Teller or crystal field splitting type. It's known that these are not reduced, they're not reproduced at an LDA GGA level. Yet some distortions are represented very well. Is there common wisdom on when GGA can or cannot describe? That's a really good question. I was a little bit lucky in this case. So when you have lead 2 or tin 2, it's actually the second order Jahn-Teller effect. So it's not that you have a partially occupied state that's been split by some on-site, by by correlation to give you a filled and empty states. It's that you get some coupling between filled and empty states that results in a much much more, yeah, the physics is, it's a little bit more easy to describe at the LDA GGA level. So this relates to the stereochemical activity or inactivity of the lone pairs. So I think if you're dealing with systems like certain transition metals, it wouldn't do a good job here. But because it's led to, I think in this case, it ends up being reasonable because it's this second order Jahn-Teller effect. So I think it's quite a special case. So Li Jiang asks, what's my view on, oh, the questions keep jumping. What's my view on machine learning's future to provide more mechanistic scientific details, matching those from DFT rather than prediction/engineering? So I think that's one of the other streams of research. I think somebody mentioned some of the deep learning work on trying to replace the many-body Schrodinger equation. So there's work, I know there's a lot of work at DeepMind. So DeepMind in London have hired a number of graduates from condensed matter physics in Imperial, I know, as one example, that have been working on this type of problem. So I would not be surprised in the next 5 years if we see a Nature front cover where the Schrodinger equation has been replaced by a deep learning model in terms of the accuracy and generality of predictions. So it's replacing these PDEs by a very large neural network. And of course, a lot of effort is going to go into the training of that. I think the question is, once it's trained, will that be shared? And are we going to be doing fewer and fewer DFT calculations? And again, I think it's going to depend on the property that you're interested in. So maybe if you care about energy or some simple property, that's fine. I think there's still a lot of effort going to having more sophisticated response functions, for example, optical properties or magnetic properties, where we will still have development using the traditional methods. And I see Anubhav has joined back in. So yeah, are we running out of time?
We're a few minutes over time at this point, and there's still quite a bit of questions to go. So my suggestion is maybe we do a couple more questions, and then anyone whose questions were not answered, maybe they can post them on materialsproject.org/seminars, and then we can try and have a community discussion afterwards for some of these other ones. So Aaron, I'll leave it back to you, but I realize we're kind of over time now, so we might just want to do one or two more.
Okay, yeah, it's sort of dinner time in London, but thanks for all the questions. Let me just answer two more, and then I will try to answer the rest online if you have them. So am I aware of any methods looking into electron excitations or electron phonon coupling on the energy of materials at finite temperatures? What I've seen is, I think separately, in the quantum chemistry community, people have definitely been working on models for dealing with electronic excitations. So going beyond DFT and trying to train on sort of higher order sort of post-Hartree-Fock methods. Separately, I think we've seen that machine learning models can reproduce phonon density of states quite well. But I haven't seen anything that's predicting for materials electron-phonon interactions. I think one of the reasons is they're quite expensive to calculate. So we don't yet have the data sets that enable training reasonable models. So I think that's one of the bottlenecks. It's generating a sufficiently large data set, but I suspect some smart people are working on that problem right now. But thank you for that, anonymous attendee. So final question from Ebi Sam. Do I expect new unknown features, maybe a combination of known features or new ones, coming up as key parameters in predicting properties, or as approximations to a reasonable range? I really hope so, because for me, that's the exciting thing, where if machine learning, training all of these models, tells us something that we really didn't know. I think for classical potentials, there's a lot of understanding of the limitations of two-body methods, that when you have a pairwise potential, it cannot describe these types of phenomena. You need to have three-body or four-body to describe. And that sort of tells you something about the nature of the interactions. But if we end up identifying some particular features that are very efficient for predicting mechanical properties or vibrational properties, and we can understand them, I think that's really, really cool. instead of just, I think the first wave of machine learning for materials was really throwing in every possible feature, all of these very random ones, like the melting point of the element, the range of the melting points, the average. Sometimes you end up getting a model that relies on that feature, but it's very difficult as a scientist to really understand, is that a meaningful correlation? Or is it just the fact that you had this random feature that's giving rise to a slightly better model? So I am very, very hopeful. I think we're going to learn a lot in terms of the features that end up performing well for particular classes of property. And I think that's the last question. So thank you all for being so engaged, for asking. And yeah, I see Annabelle is back.
Great. So thanks so much, Aron, for the talk and for staying extra in terms of answering the questions. The link to continue the discussion in case you have further questions is in the chat right now. So please check that out. Thank you again, Aron, and we look forward to seeing everybody at the next Materials Project seminar.